Look at this. A simple iron nail, wrapped in copper wire, hovers over a pile of paper clips and instantly snaps them up. But the moment we disconnect the battery, the clips crash back down to the table. The magnetism simply vanishes. To understand where that magnetism went, we have to look at the wire itself. When an electric current flows through a single, straight piece of wire, it creates a magnetic field. But as you can see in this diagram, that field is incredibly weak, barely enough to affect a nearby compass needle. However, if you take that exact same wire and wrap it into a tight coil, those weak individual fields overlap. They merge together, multiplying their power into a single, highly concentrated magnetic force. That coiled wire alone is strong, but to really multiply its power, we place a specific material right in the center, a soft iron core. Let's zoom in on that iron. Inside unmagnetized soft iron, the atoms act like tiny individual magnets. As this diagram shows, they are completely disorganized, pointing in random, chaotic directions and canceling each other's magnetic pullout to zero. That changes the millisecond we run an electric current through the surrounding wire. The electrical flow acts like a drill sergeant, forcing all those chaotic iron atoms to instantly snap to attention in perfect parallel alignment. But the true advantage of soft iron reveals itself when we cut the power. Without the current holding them in place, the atoms immediately scramble back into their disorganized, non-magnetic state. This ability to align on demand and scatter just as fast allows engineers to build electric door locks that grip tightly when powered and release instantly when you swipe your card. Now that we have a temporary magnet, the engineering challenge is scaling it up to do heavy industrial work. We have 3 main dials we can turn to increase that strength. The first dial is simply the geometry of the wire. We can add more turns around the core. Look at this comparison. On the left is a sparse 10-turn coil. On the right, a dense 50-turn coil. Because there are more overlapping loops, the 50-turn coil generates a massively larger and denser magnetic pole. The second dial we can turn is the electrical flow itself. We can pump a higher magnitude of current through the wire. By upgrading the power source to push a thicker, more intense current, the surrounding magnetic field is forced to expand proportionally. More electricity directly equals more magnetic muscle. The third and final dial is the material we choose for the electromagnet's internal core. We could try aluminum, but it refuses to magnetize at all. We could try hard steel, but steel retains its magnetic alignment even after the power is cut, meaning it would pick up a heavy load and then refuse to drop it. Soft iron wins this industrial shootout every single time. It provides massive magnetic strength while maintaining perfect on and off control. When you max out all 3 dials, thousands of tight wire turns, a massive surge of current, and a giant soft iron core, you get electromagnets like this one. This crane uses those exact principles to pick up and drop scrapped cars. Scaling these same 3 variables creates the immense, deeply penetrating, and safe magnetic fields required for an MRI machine to scan the human body. There is one final element of control. Just like the permanent magnets stuck to your refrigerator, an electromagnet possesses distinct north and south poles. Here, electrical current flows uniformly in one direction, creating a default state with a static north pole at one end and a south pole at the other. Watch what happens when we reverse the battery. The current flows backward, and the magnetic poles instantly flip. Polarity is not a fixed physical trait of the metal. It is a highly controllable feature dictated entirely by the direction of the electricity. To see the real-world power of reversing those poles, we just need to look inside a standard loudspeaker. Inside your speakers, alternating electric current forces an electromagnet to flip its poles thousands of times every second. In cross-section, the flickering electromagnet rapidly attracts and repels against a permanent magnet behind it, forcing the speaker cone to violently vibrate. These vibrations push the air, creating pressure waves. That sequence of reversing polarity creates the music we hear. By mastering the existence, the sheer magnetic strength, and direction of electromagnetism, we took an invisible natural phenomenon and engineered it into a universal tool.